Let's talk about power series. You can see on the screen here the definition of a power series centered at A. It's a series of the form C sub n x minus A to the n. All right, so this looks worse than it is. So the Cn part of this is a formula. So it's going to be, n over n plus 1 or 1 over n factorial. That part of your power series is going to look like the terms of just a regular series from before. The A value is the center of the power series. And in each particular power series, the A will be filled in with a number. The n here, sometimes it's a k, but we'll see it more often as an n. This is the index in the sigma notation. So in the formula, this truly is an n, so that in individual terms, you've got 1, 2, 3 in that spot. The x is the big difference between a power series and just a regular series. So the x in each of our power series is literally the letter x. So in each of these terms, you have essentially a variable. So a power series, once you write it all out like this, is sort of like an infinite polynomial, where you have ascending powers of x, you've got coefficients. That's actually why we use the letter c right here. It's c for coefficient. And you've got powers of x, and it's not a polynomial because it never ends anywhere, which is why we think of it as an infinite polynomial. All right, so let's see two examples of power series. I've got them already written on the page here. So our first power series is on the left. We'll have the sum n equals 0 to infinity of just x to the n. Now this looks like a really, really simple version of a power series, but it still counts, right? So we have n is the actual index and x is sort of like this input variable. Technically here, the Cn is just 1, so we just don't see it. And then the A value is 0. So if we were asked what's the center of this power series, we would say, oh, the center A is just 0 because I'm not subtracting the number. Whereas in this power series over here, it fits that definition a lot more. So here we can see the center A is 5. You can see the 1 over n is your Cn formula. All right, so let's go back to this first example and actually spell out the terms, right? So we can see this in sigma notation, or we can write out the terms of the power series. So if we plug in n equals 0, we get x to the 0, which by convention, we're always going to assume anything to the 0 is 1. Even though technically if x is 0, you would have 0 to the 0. Our convention is just anything to 0 is 1 in this context. And then we would add. The n equals 1 term is just x. And then n equals 2, n equals 3. And this version of my power series is really showing you the infinite polynomial situation. So for this power series, if we choose to plug in a value for x, we create one single just regular series, which either converges or diverges. So we can pick random x values. Let's say x equals -2. I'm just picking random numbers here. If I plug that into my power series, I'm going to put a -2 where the x is in this formula. So I get -2 to the n. And that creates just a regular series. So that's 1 minus 2 plus 4 minus 3, and so on. We could also plug in a fraction. Let's say we plug in x equals 2/3. Our series becomes 2/3 to the n, which again is just a regular geometric series. We get 1 plus 2/3 plus 4/9, and so on. We can also do this with the example on the right. Everything's a little bit messier and more complicated, but it generally works the same way. This series starts at 1 because the 1 over n formula can't have a 0 plugged in. That's okay, even though there's a 0 in the definition here, it's not a power series if it has to start at a different time. Typically, power series either start at 0 or 1 for exactly this reason. Right. So if we spell out a couple of the terms here, we would have 1 over n, so that's 1 over 1, x minus 5 to the 1 over 2, x minus 5 squared, and that's all I can fit on my page, so we'll say dot, dot, dot. The next one would have a 3 in both those spots, and so on. We can still plug in values of x here as well, and it becomes one particular series. So a power series, you can think of it as an infinite polynomial. You could also think of it as kind of a family of series. Right. So let's plug in x equals 10. So the x right here in the formula is a 10. So I have 10 minus 5 is 5 in this spot. So my series would be n equals 1 to infinity, 1 over n, 5 to the n. If I plug in, let's say x equals -3, I still have 1 to infinity. A -3 plugged in for x right here makes -3 minus 5 would be -8. So we have 1 over n, -8 to the n. And I've created an alternating series with that negative number then. So this brings us to a couple definitions I have pre-written at the bottom of my page. And I'm leaving space because we're going to come back to these examples once we think about these definitions. Okay, pause me anytime if you want to copy these down. So we have interval of convergence and radius of convergence. The vast majority of problems that you'll see in this section are asking you to compute either one or both of these items for the power series you're given. Right, so the interval of convergence, which I'll abbreviate IOC, is the interval of all the x values for which it converges. So it's all the values of x that you can pick that actually create a convergent series here. The radius of convergence, which I'll abbreviate ROC, is technically the radius of that interval, and I have a few explanations of that below here. So if your interval of convergence, so when we say interval, we mean like literally an interval of x values, so we're going to be using interval notation. So you'll see, a number, comma, a number, the first thing, comma, the last thing. And then we'll have some combination of parentheses and brackets depending on the particular situation. So if this a comma b is your interval, then the radius is 1/2 b minus a. It's exactly half the length of that interval. The radius doesn't really care if you have a parenthesis or a bracket on either end. It'll come out the same way regardless of that choice. And then another way to think of it is that the interval is the center, A. This A is this A, the center. So the interval of convergence will be that number plus and minus the radius. So essentially, the center A is literally the center of this interval. And I guess I shouldn't have used A right there because these are not the same. All right, let me change it. We'll change this A into a C because it's not the center. So what's supposed to be happening is that the center of the power series is literally smack in the middle, dead center between these two numbers here. So this interval is a minus a bit, comma a plus a bit. That creates that interval. And of course, the bit is the radius. Okay, so let's come back to this first example of the power series and consider the interval and radius of convergence. And we talk about this one. Right, so if you notice when we're plugging values of x in, we end up creating geometric series. These are geometric just because of the way this power series was set up. They're all geometric, with the A and the R for geometric being 1, and then the R is whatever the x value is. So we can use the rules that we know about geometric series here to talk about what you can plug in to make convergent, right? This is convergent, but this is divergent. We know that this will be convergent for the absolute value of R less than 1 And now X is playing with R. So we're gonna say the absolute value of X less than 1. If the absolute value of X is greater than or equal to 1, it's divergent. So this is all the X values in the interval of convergence. We want to say our interval in interval notation. So we might do this in 2 steps. If the absolute value of a number is less than 1, that means that that number is stuck between -1 and 1. So the interval of convergence is -1 to 1. And I'm going to put parentheses on both edges to correspond to these strict inequalities here. If you got, let's say, a less than or equal to in a different answer, you'd have a bracket corresponding in the interval notation. Okay, so the interval of convergence is -1 to 1. All those X values make this a convergent series. Anything outside of that makes it divergent. And the radius of convergence should be half the length of this interval. So the radius of convergence is 1/2 1 minus -1. So the bigger number minus the smaller number, which is 1/2 times 2 is 1. We can also think of this on a number line. -1, 0, and 1. So my interval of convergence is between -1 and 1. We can see our center is literally the center, right? So we started talking about this power series saying the center is 0. It's smack in the middle of my interval of convergence, which we said it should be. And then the radius is going to be the distance away from the center you can get in this interval. So over here, you can get as far from 0 as 1. So that's your radius of 1. And then it's the same distance to the left if you go out to the other. Okay, so if we look at the second power series example, it's a lot harder to answer the question, what's the interval radius of convergence here? It's not particularly obvious what values of X are actually creating convergent versus divergent series here. So for something like this, and for all future examples that aren't quite as nice as my first one, our trick is going to be to use the ratio test. And you can tell by how much space I've left myself that I'm not actually going to do it in this video. This is where we're going to pick up in class together. So we use the ratio test because there's no conditions to use it, right? This can be applied to any series ever. So we don't have to worry about what this might, meet or not meet in terms of conditions. And the ratio test is nice because it can conclude both convergent and divergent. So we're going to start class by taking this formula, n's and x's and all, and putting it into the ratio test to try to figure out when it's going to be convergent.